My name is Jesse Dunac, and I'm excited to walk you through my closest pair implementation in Python. So over the next minutes, we're going to go over problem motivation, two algorithm approaches, brute force and divide and conquer structure of my code. All right. So first, I will just want to lay out the problem. So given endpoints in a plane, we want to figure out the 2 points in which the minimum Eleusinian distance, and this task arises in many areas like data clustering and GIS applications, things like that. So, uh, so pretty much we just have to look at every pair that results in O parentheses n squared time. While it looks simple, it can become like really hard for big data sets. So that's why we need to like find a better solution. So that's why we do things like the brute force algorithm. So in algorithm one, we use a brute force method. It's pretty straightforward to implement. So we loop I from 0 to n minus 2, and for each I, loop j from 1 plus I to n minus 1. And then we compute the distance and track the minimum. And then another option and another algorithm that we did implement is the divide and conquer method. In this method, pretty much what we end up doing is we sort the points. So we sort the points by x coordinate and by y coordinate using a merge sort, and then we recursively split px and py at the midpoint, solving for each half, and then we compute the smaller of the two distances using distance 1 and distance 2. We build a strip of points whose x distance from the midpoint is less than d equals minimum distance 1 and distance 2, already sorted by the y. And then we just scan the strip, comparing each other, comparing each point up to 6 neighbors, updating the minimum if it's necessary. So the recursive helper never recomputes subproblems redundantly, ensuring 2 recursive calls per level, plus linear time merging and strip checking. So pretty much to measure performance, I generated random points using the unique integer coordinates scaled by n times 10 to avoid collisions for n in each like 10,000, 20,000, 100,000. I ran algorithms m is equal to 10 trials using time to record start and end times, converting to milliseconds, and I average the run times per algorithms and fit constants C1 and C2 so that it predicts the brute force time and it predicts the divide and conquer time. So the results from this experiment are in the first graph, the empirical O parentheses n squared versus the O parentheses n log n, the brute force curve grows way quicker and overtakes the divide and conquer curve, which remains like pretty much linear on this scale. And then on the second graph, the brute force empirical versus the predicted, the n squared model fits closely, confirming that the expected growth rate is validating to our constant C1. And then lastly, the brute force empirical versus divide and conquer predicted. When plotted, the predicted n log n curve lies well below the brute force measurements for a large n, illustrating the scalability advantage. And then across all trials, divide and conquer outperforms the brute force starting around like 30,000, matching the theoretical expectations. So in conclusion, the brute force method is the easiest to code for smaller data sets, like stuff that's like under 30,000 points. But the divide and conquer requires much more work, but it pays off with the O parentheses n log n performance. Also constant factors in Python mean that very small brute force may still be faster due to like overhead and stuff like that, but as it grows, divide and conquer is honestly just superior in real world applications, such as like clustering data sets, things like that. So I just wanted to thank you for listening to my presentation and have a good day.